Welcome to our first lecture on this new series, Strategic Math. In our first lecture, I would like to talk about fractions. Why would I want to talk about fractions? Because this kind of problem is interesting, and you can see it in any kinds of matches or any kind of entrance exams all over the world. To solve these questions, we have to have a clear path. And in this video, I'm going to show you how these questions can be solved. By using these methods, we can solve this question more quickly than others. Be sure to watch till the end so that you can know how these fractions are used in other ways. Before our video starts, please remember to subscribe and ring the bell to get notified with new videos. So today's question is like this. If there's only one set of answers for the equation 7 over 8 less than n over n less than 8 over 9, m and n are positive integers, what's the maximum and minimum for the number n? Before we answer our today's question, let's look at something else. How would you multiply fractions? Well, you'll multiply them by the numerator itself and the denominator itself. Like this, 2 times 4 over 3 times 5, and you'll get your answer, which is 8 over 15, and this is correct. But how would you add fractions? Well, you won't do it like this. You wouldn't do it like 2 plus 4 over 3 plus 5, which is not the correct way. So how would you do it? Well, you'll reduce the denominator to their common denominator. What you'll get is 22 over 15, which is the correct answer. But notice something. The incorrect answer, which is 3 over 4, is actually between the number 2 over 3 and 4 over 5. So is it true for every integer? Well, why not we prove it? So look at our first theorem. If b over a is bigger than d over c, where a, b, c, d are all positive integers, then b over a must be greater than b plus d over a plus c and is greater than d over c. If we want to prove this, we'll first prove the first part, where b over a is bigger than b plus d over a plus c. To prove this, we'll subtract them together. And this is what we'll get. Notice further that we can simplify it to this form. Remember one thing. The theorem tells you that if b over a is bigger than d over c, that means we get that bc is bigger than ad, which means bc minus ad is greater than 0. A times a plus c are also greater than 0 because they are both positive integers. What you'll get is that this equation will be greater than 0. If we move the equation, we'll find that b over a is greater than b plus d over a plus c. We can use the same way to prove the latter part of this equation. Before going on to explain our problem, let's look at something else. This is our practice problem for today. It has to solve for the minimum of b in the following equation, 5 over 9 less than a over b less than 4 over 7, where a and b are positive integers. So from the theorem, we can know that 5 plus 4 over 9 plus 7 will be between these two numbers. So let's presume that our minimum is actually 16. But is it? How will we prove that 16 is the minimum of b? So to answer this question, we have to talk about another thing called the Farey sequence. The Farey sequence of order n is a sequence of completely reduced fractions, either between 0 and 1 or without this restriction.
In this lecture, we'll be mainly talking about fractions that are between 0 and 1. Let's look at some examples. So f1 will be 0 over 1 and 1 over 1. Remind you that Farey sequences are in ascending order. f2 will cap the terms that f1 have, like 0 over 1 and 1 over 1, but it will add new terms, and these new terms has the denominator as 2. We'll add 1 over 2. We won't need to add 2 over 2 because this will be just equal to 1 over 1. Remember that Farey sequences have fractions that are completely reduced. Let's look at another one, f3. We'll keep these in mind, z over 1, 1 over 2, and 1 over 1. We'll add fractions with the denominator 3, and we'll make its numerator from 1 to 2. Farey sequences will be generated like this. After looking at how Farey sequences are formed, let's look at the properties of Farey neighbors. If b over a and d over c are neighbors and b over a is bigger than d over c, then d over c minus b over a will be equal to 1 over ac. This also means that ad minus bc equals to 1. This is the first property of Farey neighbors. The second property of Farey neighbor is that if b over a and d over c are neighbors, then when n increases, the next terms that first appears between these two will be b plus d over a plus c. After looking at the two properties, we'll now make some observations. From property 2, we know that if these two are neighbors, then the next term that appears will be q over p, which is equal to b plus d over a plus c. And from property 1, we know that this means that ad minus bc equals to 1. Notice that in a Farey sequence, our fractions will be from ascending order. So the next terms that first appears between these two fractions will be as small as possible. That means that we'll have our minimum of p. So this is how we derive our lemma. Let's now prove our lemma. In the equation b over a lesser than q over p lesser than d over c, if ad minus bc equals to 1, then the minimum of p is a plus c. First, we notice that aq minus bp is greater than 0, and dp minus cq is also greater than 0. If we look at q over p and multiply them by 1, which is ad minus bc, we'll get this. Notice we have aq and we also have cq. So we now try to add these words in red so that they will form this. Why would we want it to form like this? Remember that p and q are integers, and we have already proven that dp minus cq and aq minus bp is greater than 0. If p is an integer and these two are greater than 0, the only way to get our minimum is to let these two be equal to 1, which means aq minus bp equals to dp minus cq equals to 1. We can get that the minimum of p equals to a plus c and the minimum of q equals to b plus d. The next thing we have to prove is that q over p is a completely reduced fraction. To do this, let the GCD of a plus c and b plus d equals to k. This means that k will divide a times b plus d. K will also divide b times a plus c. If we subtract these two, we'll get that k will divide ad minus bc, which in this case is 1, If k divides 1 and k is an integer, this means that k equals to 1, which means that a plus c and b plus d is coprime, which means that a plus c and b plus d is coprime, proving that q over p is a completely reduced fraction. After this lemma, we can now look back on our practice problem. Notice that 9 times 4 minus 7 times 5 equals to 1. This means that our minimum of b is really 16. So let us look back on our question today. We can easily see that 8 times 8 minus 9 times 7 equals to 1, which means that our minimum is 9 plus 8 equals to 17. But what about our maximum? Well, to answer this question, we'll have to dig in further. By multiplying these three fractions with m, and after canceling the two m's, we can get that 7 over 8 times m is lesser than 8m over 9. Notice that the question said that there is only one set of answer, and there's another trick. N must be an integer. So let's draw it on number line, where 7m over 8 is here and 8m over 9 is here. Then n must be somewhere in this region. We said that there is only one set of answer, which means that the length of the region must be lesser than 2. Only this can get that there are only one set of answer, but because if it is greater than 2, then there must be two integers in this region. What we'll get is that 8m over 9 minus 7m over 8 will be lesser than 2. We can reduce them to the common denominator and get that n is lesser than 144. This means that our maximum for n is 144, and that's how we solve this problem. So time for our conclusion for today. In the equation b over a lesser than q over p lesser than d over c, if ad minus bc equals to 1, then the minimum of p is a plus c. If there's only one set of answer, the maximum of p will be 2ac over ad minus bc. Remind you that you can still use the second conclusion to solve for the maximum of p even though ad minus bc does not equals to 1. And that's about it. Here's another problem that I want you to think. It has to solve for the minimum of b in the following equation. 47 over 151 lesser than a over b lesser than 34 over 109. A, b are positive integers. So you can clearly see that 151 times 34 minus 109 times 47 does not equals to 1. So how will we solve for the minimum? Well, be sure to watch our next lesson because we'll talk about it in our next lecture, the same idea with continued fractions.
Thank you for watching the whole lecture. In the end of this lesson, I would like to talk about how Farey sequences are used. So an interesting thing about Farey sequences is that it can be linked with four circles. Remember that I said that in this lecture we only talked about fractions between 0 and 1. But four circles can have fractions well over 1 and lesser than 0. The interesting thing with four circle is that when we draw these fractions on a number line and we get a point where q over p, we draw a circle on the number line, and this circle have a radius of 1 over p squared. The interesting thing about these circles is that when you draw the circles of every Farey fractions, you'll find that these circles will be tangent with each other. They will not overlap, and they'll also not intersect. If you want to learn more about these things, I'll put the link down in the description. You can watch the video made by Numberphile. I think that their explanation on 4 circles are great. There are also other many kinds of properties with Farey sequences, and you can explore them on your own. In this video, I only talked about a small part of Farey sequences, and I hope that you can use this small part on many kinds of problems. And in the next video, I'll talk about continued fractions, how we can use continued fractions to solve this same problem. Thanks again for watching this lecture, and remember to subscribe and click the bell. The next video will be on 2 weeks later, Friday 9 p.m. Be sure to stay tuned and watch the video. And that's about it. I'm Raymond Lin, and this is Strategic Math.